And now we're on to enzymes video 3. So we know that we have digestive enzymes which are involved in catabolic reactions, and we know that the substrate needs to be a very, very specific and complementary shape to the enzyme. And if it's got the sufficient kinetic energy to collide with the enzyme, then we get the enzyme substrate complex and we form a transitional state which has the effect of lowering the activation energy and allowing the reaction to proceed and to produce a product. And the product for digestive enzymes are smaller biological molecules than the original substrate molecule. So the next thing for us to consider is more to do with the shape of the active site and the sensitivity of the enzyme. So these are the syllable statements from the IGCSE specification. We need to understand how the functioning, the job of the enzyme is affected by temperature. And we also need to look at the effect of pH. Now, the first thing I want us to consider is an egg, and hopefully all of you have had the experience of cracking open a raw egg, and if you do and then you throw it into a pan, you know that you can produce a fried egg which is nice to eat. Now the white of the egg all the way around here is called albumin, and albumin is pure protein. And remember that enzymes are made of protein. So this is again a model, an analogy to help you to understand things a little bit more. So the albumin of an egg is good to eat. It's not an enzyme, but it is made of protein. When you crack the egg, you'll be familiar with the idea that it's transparent, gelatinous, sort of viscous liquid type of material. But when it hits the pan, it changes its shape very significantly. It becomes much more solid, and it changes its color to white. Now, when we cook the egg, when we cook the albumin of the egg, the white of the egg, what we are doing is we are changing the shape of the enzyme. We are actually doing denaturation of the protein. So we're denaturing the protein albumin when we're cooking the egg, and the albumin, because it's made of protein, allows us to think about what might happen if we expose enzymes to too much heat. So if you take an egg and you crack it and you put it into ice, nothing happens. So enzymes, like the albumin here, are not sensitive to cooler temperatures, but if you heat the albumin up by putting it in a frying pan, what happens is that the albumin changes its shape significantly. The protein denatures. In the same way, enzymes, if you cool them down, don't stop working, but if you heat them up, they change their structure so significantly they become denatured, rather like this egg here, and they are kaput. They won't work again at all. If I took an egg and I was to crack it into acid, what would happen is that, and this would look like a cooked egg. The acid would change the shape of the albumin and denature the albumin. In the same way, if you took an enzyme and you put it in very, very acidic conditions, it would denature. It would become very, very different in structure, and it would change its shape, and it would no longer be able to function. If I was to crack an egg into bleach, which is a very, very alkaline solution, what would happen again is that we get this denaturation process. So all proteins, whether they're enzymes or not, are sensitive to high temperatures or heat. They're also sensitive to extremes of pH. And when any protein molecule, including enzyme, is exposed to heat or extremes of pH, it will change its structure. It will denature. And when it denatures, this is a very, very permanent change of shape. And if we think about that in the context of an enzyme, we can see why it is that enzymes need to be kept at the very, very correct temperature. So here we can see the shape of the active site, and here we can see the shape of the substrate. And if this substrate can collide with this active site, then we're going to get a reaction taking place. So this is going to work. Okay, this is a functioning enzyme, and we've got the complementary shape of the substrate with that of the active site. If we start to heat up an enzyme, in the same way as if we start to heat up the albumin of an egg, what happens is denaturation, a permanent structural change in the protein. So this is a denatured enzyme, and if we have a denatured enzyme, this substrate is no longer the complementary shape with the active site, which means that this substrate is not going to get broken down by this enzyme. The enzyme is permanently going to be unable to function. So denaturation is when we take an enzyme or any protein, but enzymes are made of protein, and we change the shape such that it causes a permanent change in the structure, which means it's no longer able to work. So normal enzymes have a very specific complementary shape to that of the active site. If you heat them up or you expose them to extremes of pH, they change their shape, which means they're denatured and they can no longer work. Now, when we go back into school, we're going to be able to do some actual hands-on experiments where we take an enzyme and we place that enzyme at very, very different temperature levels, and we can track the rate of a reaction. And when we do that, when we go back to school, we're going to get a graph which looks something like this one. So at very low temperatures, we get a very slow rate of reaction. Now, the reason here is that at low temperatures, we're not giving much kinetic energy to the substrate and the enzyme, so they're not moving very much. And if they're not moving very much, then they can't collide, they can't form that transitional state, and the reaction can't proceed. So at very low temperatures, enzymes work very slowly. There's a slow rate of reaction. As we increase the temperature, then we increase the kinetic energy, we increase the number of collisions between the enzyme and the substrate molecule, and therefore we increase the rate of reaction. So here is the so-called optimum temperature. The optimum temperature is the temperature at which we have the fastest rate of the reaction here. Now, if we go beyond that optimum temperature, what starts to happen is that the enzyme starts to vibrate. It's got so much kinetic energy that the internal bonds within the enzyme itself starts to vibrate. They start to change its structure, and we get a very, very swift decline. And here we have denatured the enzyme. So anything which is below optimum temperature will mean that the reaction will be slow. Optimum temperature gives you the fastest rate of reaction. Above optimum temperature means that we start to denature the enzyme. And denaturation is a permanent structural change in the enzyme, which means the active site is no longer complementary to the substrate and it can't work. If we cool the enzyme down, it's still not going to work. It's a permanent change. Again, also when we go back to school, we're going to do similar experiments to look at the effect of pH. And when we do that, we're going to get a graph which looks something like this. So if we've got very acidic or very alkaline pHs, then we get a very low rate of reaction. So if it's very acidic, that the enzyme will denature, it will no longer work. Here what we've got is the optimum, the fastest rate of reaction, and for most enzymes, the optimum pH is going to be pH 7. It's not always true, but it's mostly true for most enzymes. And then if we go to extreme here and we look at the alkaline pH levels, then we can see that the enzyme denatures. So extremes of pH are going to denature the enzyme, and then we've got the optimum pH, and the optimum pH is when the enzyme is working at its fastest. Now, in humans, and this is not true of all organisms, but in humans, the optimum temperature is around 37 degrees. So 37 degrees is body temperature, which is why this is optimum for our enzymes to work. And the optimum, as I said already, for most enzymes, including the enzymes in humans, is pH 7 in the middle of the pH scale. This next graph is something which, again, goes a little bit beyond your specification, but it's quite interesting for us to think about, and that's the effect of substrate concentration. So if we've got a little bit of starch, then the rate of starch breakdown is going to be low. If we increase the amount of starch, then we're going to increase the rate of reaction until we get to here. So here, if we increase the starch beyond this particular substrate concentration, if we've got more starch, the reaction cannot happen faster. And that's because we've only got a finite quantity of enzyme, and we need the starch to fit in the active site, to be broken down, to release the product, maltose, and then be free to take the next starch. So here we say that the enzyme is saturated. So increasing the substrate concentration increases the rate of reaction, but then we get the enzyme being saturated. It's working at its maximum, okay, and we need to turn over the substrate and free up, because remember, enzymes can be used over and over again. So increasing the substrate concentration beyond here is no longer going to give you an increase in the rate of reaction. So your next job is to think about everything I've said, have a look at your textbooks and add some notes together. I also want you to have a go at task 2. That should say blankety blank. And blankety blank is on page 3 and page 4 of your booklet. So if you look at page 3 and page 4 of the booklet, you can see paragraphs there where you need to fill in the blanks. There's a word bank to help you if you scroll down to the bottom of task 2. I also want you to have a look at this grid. This table is found on page 8. So I want you to do task 2, which is on page 3 and 4, and then the table on page 8. Okay, thank you.